guys. My name is Mark, and I'm an undergraduate student who's doing some research at Jimmy Moore's lab. Today, I'll be talking about the characterization of the contractile phenotype in cultured lymphatic muscle cells. So, just a little bit of background about the lab I work in and my project. So, Jimmy's lab mainly focuses on the overall biomechanics and mathematical modeling of pumping and lymph flow in lymphatic vessels and lymphatic networks. So what my project focuses on, it's a scaled down method. So I look at the individual contractile units, so the lymphatic muscle cells. So the first thing I actually want to mention is in previous presentations, I saw people mention lymphatic muscle cells as smooth muscle cells. That is actually incorrect. These cells are hybrids. So they're hybrids of skeletal, smooth, and cardiac muscle. So, for example, they possess myofibrils, which are seen in skeletal muscle, high concentration of proteins, cardiac proteins such as cardiac alpha-actin in cardiac muscles, and the general morphological, so spindle-like morphology that you see in smooth muscle cells. So now let me just quickly address the problem that I'm looking at. So this is applicable to all muscle cells. So what you see is that when you essentially extract and isolate any muscle cell and place it on a culture dish, it differentiates quite quickly. It takes a couple days. So it turns from a contractile muscular phenotype into a synthetic non-contractile proliferative phenotype. And so we try to combat this problem as well as simply just look at these cells in the stage where they are still contractile. And so we're really, in the end, ultimately we're trying to find a link between this problem, so this loss of contractility, to the overall macroscale loss of or dysfunction of lymphatic pumping, which you see in clinical lymphedema. And so the aim of that is then to maybe even improve or replace conventional therapies. So now let me get into some background. So the first problem, again, is how do we isolate these cells? So nobody has actually really done this before, so we have to start from square one. So we get our samples as lymph nodes and collecting vessels attached to those lymph nodes from patients that undergo ovarian debulking, so ovarian cancer debulking. So we quickly transport them in some buffer and to the dissection room, and then we need to extract and isolate the cells from the tissue. So generally the methods to extract muscle cells are an explant method where so here are the actual collecting vessels. You take a little piece of the collecting vessel and you simply just place it on a dish, and in a couple days you see proliferation of cells. So as I stated before, in a couple days if cells proliferate, they're not contractile anymore. So we can't do that. So what we do is we use enzymatic digestion. So lymphatic vessels are especially tough. So we need a high concentration of collagenase as well as some elastase because they do contain elastin, and so we use our mixture, our enzymatic mixture, to perform a long-term digestion. Long-term because, again, the vessels are very tough. And from there, we're able to get a high yield in an amount of time or in a time span where we still have a contractile nature. So then the last problem we need to address before culturing these cells, or that we needed to address, was what substrate are they going to be sitting on? So, you have fibronectin, gelatin, etc. So we looked at the integrants of these cells, specifically the alpha-7, beta-1, and the alpha-2, beta-1 integrants. So integrants, as we know, are transmembrane receptors that connect the extracellular matrix to cytoskeletal elements. So actually, alpha-7, beta-1, and alpha-2, beta-1, they connect the contractile machinery to the extracellular matrix, specifically laminin 211 for alpha-7 beta-1, and it's not shown for alpha-2 beta-1, but that connects to collagen 4. So we use those as a substrate because those substrates are shown or have been shown in the past to prevent this differentiation and to maintain a contractile phenotype. So then just some primary qualitative analysis. So the first thing you really look at is, does it have a spindle shape? And you can see here, this is a very, very typical shape of muscle cells or smooth muscle cells. And so on the outside, externally, the lymphatic muscle cells, they look very similar. So then we stain for very prevalent smooth muscle proteins. alpha smooth muscle actin and SM22 alpha actin. So you can see the SMA stain here, SM22, composites, and then we look at another smooth muscle protein, SM calponin. So the stains aren't shown here. We look for cardiac proteins. So as I mentioned before, cardiac alpha actin, and then skeletal muscle proteins as well as smooth muscle actually. The alpha-2 and beta-2 isoforms of myosin or skeletal and smooth muscle myosin heavy chain. These have been shown to be prevalent in mesenteric lymphatic vessels. Then we do some more quantitative analysis with Browning Westerns and immunohistochemistry. So now let me actually move on to the interesting stuff. So what we do is we exploit a phenomenon that basically when you have an increase in transmural pressure, your lymphatic, or in general your muscle cells, they respond by counteracting this stretch with calcium-induced contraction. So you can actually see in the video, we created this custom-made bioreactor, which stretches and compresses the cells just like in physiological conditions. Here, that's just a quick strain field that's shown, and we can show that this strain field as well as the displacement field is very uniform. So we use this to stretch our cells. So then, as I talked about contraction, we need to look at the chemical methods behind this contraction. So the first thing I need to mention is that we use a very low stiffness polyacrylate hydrogel to let the cells freely contract. Then, as an actual agonist to induce the contraction, we looked at substance P, which is a very potent vasoconstrictor, an alpha-adrenergic agonist, epinephrine, and specifically we looked at high potassium, high calcium solutions, which is a universal agonist for smooth muscle cells. So you can see here, this is a stain for cagnin 1C, which is an L-type calcium channel. And we can see that actually in cells that already look differentiated morphologically, you see very low expression, but you see in these spindle-shaped cells, you see high expression of cagnin 1C, as well as over here. So then, if we do get these contractions, how do we analyze the contractions? So as I said before, we have embedded microbeads in the bioreactor that we built, and the cell, when they contract, they emit contraction forces. So we can actually measure these displacements with 2D strain tensors, and then we can use the mathematical modeling to find the vertical strain and then the overall strain with inverse finite element analysis. So I don't actually have a lot of time, so I'll just talk about this last point quickly. So before, people only measured traction forces in tonic contractions. We are able to actually measure phasic contractions using live imaging, and we're able to get these relationships. So we're able to get shortening velocity, force velocity relationships, and length tension relationships, which are very, very useful for mathematical inputs to models that other people in my lab are actually working on to mathematically model these cells. So quickly, just want to mention that we want to look at these cells genetically as well. So we want to run a full transcriptome analysis. So the problem that I addressed earlier is that the extraction method for these cells is actually very crude with enzymatic digestion. So we get a very heterogeneous sample. So what we want to do is that after enzymatic digestion, we want to use magnetically activated cell sorting, specifically targeting alpha-7 integrins with magnetic beads, and which then we will perform single-cell RNA sequencing. And then in the end, ultimately, we want to look for overlaps in this these hybrid expression patterns, so the smooth cardiac and skeletal muscle expression. And so, so overall, we want to get this top-down approach from mechanical characterization down to molecular characterization. So, thank you. Sorry.
Thank you so much. I think we've only got time for one very quick question. Peter.
Have you looked at the effect of calcium channel antagonists on the performance of these cells?
So like beta-adrenergics?
No, like calcium channel antagonist, like lymphatics.
That was actually we're actually going to start looking into that. Yeah. we look through literature and we do one.
I ask because clinically it's probably the first indication for hypertension,
Yeah.
and many of the patients get peripheral edema, which is likely to be from paralysis.